work and energy. Here are your primary questions. Let's start with the definition for work. Work is the amount of energy that one object transfers to another by applying a force over a distance. And we are going to keep this simple by saying that this force is applied in a specific direction over a very specific distance in that direction. So this is equivalent to our displacement. If you look at these three examples, we are pushing a cart up a ramp. The ramp is at different angles. So the ramp is bringing the cart to the same height over a greater distance, the smaller the angle becomes. So the height is the same, but the total distance traveled is different. And what you'll notice here is that the force requirements are different depending on the angle. The displacements also change, but the work done is the same. So the total work done in each of these examples is the same. Even though the force is different, the displacement has also changed, and it has made the work done in joules to be equivalent. We're going to talk a little bit more about that. So with the equation, we have work is equal to force times distance. And really, this is the displacement that we're talking about here. So work is equal to Fd cosine theta. And so this is going to be the equation that we're going to be working with. And the reason why it's Fd cosine theta comes down to this. And the reason for this is because the force will not always be in the same exact direction as the displacement. And so not all of the force will be used to move the object. We only use the component of the force that is in the same direction as the displacement. And so that's when we use the F cosine theta, as long as our angle is measured from the displacement vector. And since it's the work is equal to force times displacement, we have work is equal to the Newton meter, which we have defined as the joule. So that is our unit of work and what we also call energy. Now, work is a special scalar. The term that, or phrase that we use for this is a vector dot product. And what that means is the direction is important when you're doing your calculation to figure out what the work value is. But once you do that, the work, or energy in this case, itself is only a scalar. So it uses two vectors, but it becomes a scalar through the calculation. And so when you look at these examples, again, the direction is important. And so when the displacement and the force are in the same direction, so the same direction, we are at 0 degrees. Cosine of 0 is 1. And so when we look at this, this would just become work is equal to the force times the distance. And that's it, because your cosine of theta is 1, so it's just W equals Fd. In the next example, we have the displacement and the force going in opposite directions. And at first, this seems really confusing until I show you an example. So if we have an inclined plane here, and let's say you are trying to push a car that has stalled up a hill, or in this case, up a ramp. If you're not strong enough, or if your shoes don't have enough traction, you will be applying a force up, but the car's weight might be able to overcome your strength and your traction, and you'll actually be going down even though you're applying a force up the hill. So in this case, your displacement is backwards, and your force is forward, up the hill, and so it's 180 degrees, and the cosine of 180 is -1. So you are doing negative work in this case. So opposite directions, negative work. For the next example is when they are perpendicular to each other. And you can think back to independent vectors. And so just for the math, before I talk about the example, cosine of 90 is 0. So if the force and the displacement are perpendicular to each other, this goes all the way back to independent vectors. They don't influence each other. And so there is no work that is done, even though there is a force and there is a displacement. The directions do matter, even though the final answer is only a scalar product. And so the example here is, let's say you come back home from the grocery store. You pick up your groceries. You'll do work to do that, to pick it up. But as you are carrying it from your car to the kitchen, the force that you're applying to the bag is up, but the displacement of the bag is in the horizontal. So in this case, just moving the bag, so you're keeping it at the same height, moving the bag is no work that has been done. So let's talk about a new term, power. And power is related to work. It's not the same, but it's related. It is the rate at which work is done. And so we can say that this is the work to time ratio. And so we can say power is equal to work over time. And so for work, we have this in joules, and we have time in seconds. And so this would be joules per second. And this we define as the watt. And if you want, you can bring this back to newtons and meters so that you can see how these are all related to each other. So joules and watts are what we call derived units, like what we were talking about before with newtons earlier in the term. So, a quick derivation. We say that power is equal to work over time. Work we've defined as the force times the displacement, and this is assuming they're in the same direction. And so we can replace this into the work, so it's force times displacement over time. And so we can think of power is equal to force times displacement over time. So we've just factored out the force. Displacement over time, this part is equal to average velocity, so that's just the velocity with the line over it. And so we can think of power as equal to force times the average velocity. And before I get to the next slide, I want to show you a quick practical derivation for this as well. Power is in watts. And we said that this is equal to joules per time, usually seconds. Now, when you look at the electricity that you're using for your house, they are working in kilowatts, and rather than seconds, they are working with hours. And so if you ever look at your electricity bill, what you are being charged for is the amount of energy, and the way they rate that energy is they move the hours over here, so they say kilowatt hours, and that's going to be the number of, not joules in this case, but just the amount of energy. So this is just going to be the energy, and that's what you're paying for. Energy is the kilowatt hours that you're paying for at home, and this is just using the same equation, just rearranged a little bit, so the joules is the energy, and the energy is going to be the kilowatt hours that you'll see. And here are your practice problems. You want to write these out and at least attempt all of them before class. And here are your primary questions again.